Page 278, question 1. We have a car lift of compressed air. We have one piston with a radius equal to 5 centimeters, and another one with a car on top of it, and its radius here is equal to 15 centimeters. Question A asks, how large a force must the compressed air be to exert a lift force of 1.33 times 10 to the 4 newtons? So we've got this car. It weighs this. This is in newtons. This is the force of gravity. Okay. We want to know how big of a force do I have to apply here in order for the force here to lift the car? Okay. So the whole idea is I need to apply a large enough force, larger than this number. This is the force of gravity pushing down on this piston. And I need to provide a large enough force here so that this car goes up. Okay. Now, Pascal's law says the pressure that I apply to this surface has to be the same as the pressure that's applied to this surface. Those two pressures are the same. That's Pascal's law. Pressures must be the same. So, pressure is the force over area. So it's how much force you are applying per unit area to an object. Okay, so you can apply a large force to a large area or a small force to a small area and get the same pressure. So Pascal's law says, well, the pressure here, P1, has to be the same as it is here, P2. Pascal's law says P1 has to be equal to P2. Pressure is force over area. So let's look at P1 first. P1. I apply some force, and that's what we want to know. How big is that force over a certain area? Now, the question doesn't give us exactly what the area is, but it tells us what the radius is. So if we have a circle, a piston, which is a circle, and our radius is 5 centimeters. Okay. The area of that circle is pi r squared of any circle. So we sub in 5 centimeters to give us the radius. Sorry, to give us the area. So now we can take this and say, okay, that must be my area for my first piston. Now let's look at our second one. The radius is a lot larger. The radius is, instead of 5 centimeters, I'm going to put 15 centimeters squared. Pi r squared. Now the force that we want to provide is this. I mean, anything larger than this force in this car is going to go up. That's the force of gravity pulling down, right? We have force of gravity, which is 1.33 times 10 to the 4 newtons. And as long as we provide a force that's larger than this value, this car is going to start accelerating up. So we want to know what's the minimum, what's the smallest amount that I could apply just to just to get this car moving up. So if we say 1.33 times 10 to the 4 newtons, anything more than that, and this car will start going up. So again, Pascal's law says the pressure must be the same on any surface in a closed on any surface when you have a closed fluid like this. So P1 is equal to P2. So we have F all over 25 pi centimeters squared is equal to 1.33 times 10 to the 4 all over 15 squared. You can put in your calculator, it's 225 pi centimeters squared. So if I want to solve for this force, there's a couple things I can do. You can just cross multiply, or you just bring this up here, and then you divide out the pi's. I'll do it the long step. So what I can do is cancel out both pi's from each side of the equation. What I'm actually doing there is multiplying both sides by pi. Pi divided by pi is just 1, so they go away. Pi divided by pi is just 1, so they go away. So then I'm left, I can write F is equal to 25. I'll bring the units with me to show you that they cancel. 1.33 times 10 to the 4 all over 225 centimeters squared. Okay, my centimeters squared is going to cancel, and my units are just newtons. That's good. That's what we want. So if you multiply these numbers together, you should get 1470, about 78 when you round. All right. Now, this is a very important result. Look what we did. We applied this much force. If you apply that much force over here on this piston, okay, you're going to get this much force. Now let me write this. That's 133, 1, 2, 0, 0, 1, 2, 3, 4 newtons. Look at this number. We have 13,000 newtons. Over here we have 1,478 newtons. Clearly this one's a lot larger than this one. So what it's saying is I don't have to apply as much force over here in order to move this up. And the reason is the areas here, the pressures are the same. That doesn't change. The pressures are still the same. Now here's the trick. If you're doing this in real life, you would have to move this down a lot farther for this to move up just a little bit. Okay? If you think about how much volume of water is in this section versus how much volume of water is in this section, you'd have to move this all the way down just to get this to move up a little bit. So the amount of energy that you do provide over here is the same as the amount of energy that you would get out over here. But what's the same, or what's different, I should say, is the two forces. Those are going to be different numbers. So you can see how this might be useful.